A few other examples will help illustrate this. Let's look at some familiar functions, e to the x, cosine of x, and square root of x. First of all, for e to the x, let's compute the first order variation by evaluating it at x plus h. Now we know that e to the x plus h is e to the x times e to the h. And although this is a little bit of circular reasoning, we know what e to the h means. That's really 1 plus h plus terms of higher order in h. So if we expand this out, we see that the constant term is e to the x. The first order term in h is e to the x times h. All other terms are higher order in h. And from this simple computation, we can see that the derivative of e to the x is e to the x. It's the coefficient in front of the first order term in h. Likewise, for cosine, what happens when we look at cosine of x plus h? Well, we can use the summation formula for cosines and expand this as cosine of x times cosine of h minus sine of x times sine of h. And again, using what we know about cosine and sine, we can expand the terms in h and say that cosine of h is 1 plus big O of h squared, and sine of h is h plus big O of h cubed. Now, if we take these terms and rearrange them a little bit, we get a 0th order term of cosine of x, as we must. The first order term has as its coefficient in front of h negative sine of x, the derivative of cosine of x. For the square root, we have to simplify the square root of x plus h. How do we do that? Well, if we factor out a square root of x, what is left over is 1 plus h over x, all to the power 1/2, or the square root of it, if you like. I write it in this form so that we see the binomial series come into play, and using that binomial series gives us an expansion of 1 plus 1/2 times h over x plus something in big O of h over x quantity squared. Now, if we expand that out, we see that the 0th order term in h is, of course, square root of x. The first order term simplifies to 1/2 x to the minus 1/2 times h. And from that, we see the derivative. Now, notice that all of the higher order terms involve a square root of x and something in big O of h squared over x squared. If we want to ignore that and call that big O of h squared, we'd better make sure that x is positive. When x is 0, we have a problem. The derivative does not exist. But as long as x is bounded away from 0, we have a well-defined expansion in terms of h, and we can read off the derivative as 1 over 2 square root of x. There's a lot of notation associated with derivatives. The derivative of the function y equals f of x can be denoted in the following ways. Some of the best notation is df dx or dy dx. But there's some other notation that you might see or use from time to time, including f prime or y prime or y dot. Now, why the difference between these? Well, the best notations are those that tell you exactly which variables are changing. dy dx means the rate of change of y with respect to change in x. On the other hand, f prime or y dot can be a bit ambiguous. The dot, in particular, connotes change with respect to time. Now, sometimes you'll see a differential notation of the form df. This can be helpful, but again, remember which variables are changing. The one thing that you must never do is write something foolish like canceling the d's to get df dx equals f over x. Whew, no way. Don't get creative with your handwriting on these. Don't use a scripty cursive D. Don't use a Greek delta. Don't do anything like that, because those symbols have meanings of which you have not yet learned. Don't ever do any of this. Stick to the standard notation, please. Now, the most common examples of derivatives wind up involving rates of change with respect to time. For example, in your introductory physics, you've certainly seen velocity or acceleration as a derivative. These are derivatives of position with respect to time. But there are other examples as well. If you study current, current is related to a rate of change of charge with respect to time flowing through a wire. In chemistry, if you look at reaction rates in a chemical reaction, these are defined as the derivative of, say, a concentration of a product or a reactant with respect to time. There are many other examples of derivatives that are not necessarily rates of change with respect to time. If you look at a spring, one can define the spring constant as the rate of change of the force applied with respect to the deflection. The elastic modulus of a stretchy material is a rate of change of stress with respect to strain. If you want to know what viscosity is, or how slippery a fluid is, well, this is defined in terms of quantities like shear stress and the rate of change of the velocity of a sliding fluid with respect to height. And finally, economics consists of all manner of interesting derivatives. For example, if you look at marginal tax rates, these are defined as the rate of change of the amount of tax collected with respect to change in income. All of these are wonderful examples of derivatives.
There's so much more to derivatives than slope. Look around you. Do you see something that changes? That is a derivative. Derivatives are ubiquitous, and understanding their proper definition helps us to interpret, find, and then use derivatives. In our next lesson, we'll consider how to quickly compute derivatives.